Good afternoon, everybody. So today we're going to move on from our discussion on sound waves, and we're now going to move into this idea of light and light waves. So we're still going to use a lot of the same nomenclature that we used before when we talk about waves, but now we're going to just shift our focus out of longitudinal waves that we did with sound, and now start kind of looking at things more as transverse waves, because we're going to find out that when we talk about light, light is a form of a transverse wave. And over the next couple of days, we're going to start today kind of looking at what is light? Like, just very fundamentally, what is light? And then we're going to kind of shift off of that, really understand what is color, how do things emit light, and how is it that we can use things like lenses or mirrors to better understand how light works. Okay? So like I said, today we're really just going to start off really the fundamental principle of what is light. Okay, so before we can get to that, we need to go back just a few days, really a few weeks, when we talked about electricity. Okay, so we talked about electricity, and if we have a charged particle, it is going to have some sort of electric field around that. Okay, and if we take that charged particle and we move it, we start to produce a magnetic field. Okay, and this is essentially the fundamental idea of what light is. Because just like any other wave, we need to start with something vibrating. Okay, and as we get further into this discussion in the next couple of days, we'll look at the more specifics and the nuance of as we have an electron, right? We have atoms, and within those atoms, we have those electrons, those little negatively charged particles. And they wiggle. They vibrate at a certain frequency. Well, when that happens, when that vibration occurs, we get this thing called a photon that's released. And that photon is a charged particle. And so as that charged particle travels through space, it is going to have that electric field. And as the electrical charged particle moves, it produces a magnetic field. And so we can say that this photon is an amount of electromagnetic radiation. Okay? Now, this charged particle is kind of difficult to really discuss as a particle because we're going to find out the light, it behaves interestingly. It behaves sometimes kind of like a wave and sometimes kind of like a particle. So for the sake of this discussion over the next couple of days, we're going to discuss it simply as a wave. Okay? But we have this thing called a photon that travels through space, and as it travels through space, it has both electric wave and a magnetic wave, and these things are going to move in perpendicular fashions. Okay, so if we've got the photon moving right at you this way, the electric field might be going this way, which would mean the magnetic field would be moving this way. Okay, so those two fields are moving perpendicular to each other. Okay, so that's really essentially what light is. Anytime that we have that electron and it vibrates, it releases this particle that we call a photon, and that photon has an amount of electromagnetic radiation, and as it travels through space, we call that a ray of light. Okay. So moving on from that, when we talk about sound, we talk about the pitches of the sound. We talk about the frequency of sound and how that changes how we perceive that sound, correct? Well, with light, it's very much the same thing. And the crazy part about it is, if we look at that's electromagnetic radiation, okay, and we look at that light ray, that photon, we can see the spectrum of frequencies that it can have. It can have a really, really low frequency, or it can have a really, really high frequency. And the things that we can see with our eye is this tiny little sliver right in the middle. Okay? So if we looked at our spectrum, okay, right here in the middle, we've got this tiny little bit we call visible light. Okay? Now if we go up to a higher frequency than that, okay, anything above the colors that we can see. Okay, we're going to talk about colors tomorrow, but the highest frequency of light that we can see, we visibly see that as violet light. So anything above that, we can say we call that ultraviolet, right? Ultra meaning above, violet being the color. So anything with a higher frequency than the light we can see, we call ultraviolet. Okay, and many of you have probably heard that term UV light. Okay, so that's what we're talking about. We're talking about light that is a higher energy, a higher frequency than visible light. We call that ultraviolet. Okay. As we go even further onto that, we have another type of light that many of you have heard of. Okay? Anytime that you get injured and you go to the doctor and they need to do imaging to see what's wrong, a lot of the times the first type of image that they'll take is an X-ray. And all an X-ray is if we go from visible light, we increase the frequency, we get to ultraviolet, we go just even a little bit further than that, we have X-rays. And if we go even beyond that, if we just keep increasing the frequencies from there, we get to the highest level of energy, and we call that gamma rays. Okay, so these are the types of electromagnetic radiation that are above what we can see. Okay, and again, just like with sound, there are certain frequencies that we can hear. There are certain frequencies that we can see. But just because we can't see them doesn't mean they don't exist. So these are all the things that are above it. Now, there are also frequencies that are below what we can see. Okay, so we can go, if we go to the lowest frequency of light that we can see, we're going to call that the color red. Okay? And so if we go down just a little bit from that, we can actually take, again, nomenclature that we've already used. And so if we go below red, another way to say that is infrared. Okay? So if we have visible light, we come this way. We call that infrared light. Okay, so if you think about an infrared camera, right, and you look at something in that, you will see the heat that is coming off of something, right? Because anything that has a temperature will emit radiation, and this is the radiation that it is emitting. Okay? At lower temperatures, it's still going to emit this type of radiation, but it is a lower amount of this radiation. And just below the visible spectrum, we call that infrared. Okay, we think about that as like heat energy that radiates off of you. Every one of you has infrared radiation emitting from you right now. Now you think about it, if you increase the temperature of something, it starts to glow red, and then it might glow like orange and things like that. That's because it's getting hot enough and it's emitting higher energy, higher frequency radiation that starts to ooze into the visible light spectrum right here in the middle. Okay. So if we go down even further from infrared, we can now get down into microwaves. Okay, and many of you have probably used a microwave in your household to cook some food. Okay, so a microwave is just a type of light that is a super low level frequency that if we just started pelting your food with, that energy is going to get absorbed into the food, heating it up. Okay, and lastly, if we go any further down from microwaves, we're going to get all the way down here into radio waves. Okay, radio waves here are going to be the lowest end of the spectrum. And again, radio waves, just as the name implies, if you are listening to the radio in your car, it is because there are these radio waves, electromagnetic radiation, very, very low level energy frequency waves. They're traveling through space, and your antenna picks those up, goes through the antenna, goes into the radio. It transmits that information from a radio wave into a sound wave, and you hear the radio station. Okay? So light is very interesting because light is not just light, but by understanding light, we can understand all of these other things. Now, the really cool thing is a lot of you use some sort of technology that has some sort of Wi-Fi to it, whether it be, the Wi-Fi on your laptops, the signal that you get on your cell phones, the Bluetooth that works through your headphones. All of these are forms and different frequencies of this electromagnetic radiation, and many of them are of this lower spectrum over here. Okay, if we were using the really, really high stuff over here, it could be a little bit more dangerous. But all of your internet, all of your cell phone service, all of your Bluetooth stuff, it's down here in the really low frequencies, and so it really has no fear of harm to us, because they're too low of an energy to cause any sort of damage. A while back, there was a lot of people that were saying the 5G internet speeds that we were getting, that because of the setup of it, it was going to be dangerous, and we were going to see all these issues of cancer and all that. That's all completely false, because the only way for these things to cause the damage that people were worried about is if we're looking at this sort of energy up here, and the X-rays and gamma rays, even into the ultra, like some of the high-end ultraviolet stuff. This is the stuff that really causes damage to us. Really, the worst that can happen over here is things just start to heating up. Okay, and this is really how the microwave started. Is we were doing some research on this end of the spectrum, and a gentleman had a candy bar in his pocket, and at the end of working throughout the day, he realized the candy bar had melted, and after a day or two of this happening, he started realizing what was going on, and that was the invention of the microwave. It was actually research on this stuff for the electromagnetic radiation, looking at lower end light waves. So, okay, so that's kind of the electromagnetic radiation, or the electromagnetic spectrum, looking at this low level amounts of radiation. Okay. So let's kind of transition our discussion just a little bit now, and let's look at how different objects can interact with this light. Okay, two things that I want to look at are things that are transparent and things that are opaque. Okay, so if we have an object, okay, whether it be a solid, a liquid, a gas, whatever it is, as long as it's made of matter, we can have light come through space, because this is one of the interesting things about light, is where we kept saying that the more dense the material is, the quicker sound could propagate through it. Well, light is the exact opposite. The more stuff that's in the way, the slower the light moves. Okay, and so we have light that's being emitted from the sun, and it is traveling through space, and because it's traveling through space, there's nothing there, and so it can go as fast as it wants. Okay, and so we get to that that speed limit of the universe, the fastest anything can go. That is the speed of light. A lot of times in equations, you'll see it referred to as the letter c. You've probably seen that in the famous equation E equals mc squared. That c in there simply just refers to the speed of light. Okay? And that speed of light is at a speed of 3.0 times 10 to the 8 meters per second. So if I expand that out, it would be 3 with 8 zeros. So 1, 2, 3, 4, 5, 6, 7, 8. So we're looking at 300 million meters per second. That is our speed of light. That is how fast light travels through space. And to give you perspective of how big our galaxy is and how big our solar system is, even at this speed right here, it takes light 8 minutes to go from the sun to here. 8 minutes. So the sun could just completely disappear. It could just be pulled out of existence. And we wouldn't understand that. We wouldn't even know that for 8 minutes. Okay? Moving at 300 million meters per second. Okay, but let's kind of backtrack a little bit. So I said I want to talk about things that are transparent. How is it that a light ray interacts with something that's transparent? Well, a lot of people might think, okay, well, the windows in this room, they are transparent. So the light rays just must come through, and they just pass right through the glass into the room, and that's it, right? You might think about the atmosphere, right? The gases that we live in, they are transparent, right? So the light must just travel right through, and it just passes right through it, and that's it. But it's not quite that easy, okay? So if we've got, let's take glass for an example, okay? So if I've got a piece of glass, okay, and I've got a bunch of molecules in it, right? I just kind of draw, those are all atoms right there. What the light's going to do is it doesn't just simply just pass right through the glass, even if it is a transparent object. What it does instead is, as it comes through, it interacts with the first level, the first layer of atoms. And those atoms absorb that energy. And that absorption of energy wiggles the electrons a little bit. We'll talk about that later when we get to light emission. But it wiggles the electrons just a little bit. And that emits that photon again. And it exits out of that atom and it goes into the next one. And it gets absorbed by that one and it spits out another photon. And it does that over and over and over again until it gets to the last molecule in the glass and it emits that and it keeps moving on. Okay? And so this is the reason that if you have more dense objects, it slows the speed of light. Okay? So again, if we're in space, there's nothing for it to run into. So that's why it can travel at this 300 million meters per second. But when it starts getting to the atmosphere is not that dense. So it's still going to be going at like 99% the speed of light. As you start hitting things like water, right? Light still travels through water. Water is transparent. Okay? Water is really going to slow it down to about 3/4 of the speed of light. Okay, so still not horrible, but it slows it down a little bit more. You know, you go into something like a diamond, it's going to slow it down even more, and so on and so forth. So the denser and denser things get, the more and more it's going to slow that speed of light because it has to enter in each atom, get spit out, enter in each atom, spit out, so on and so forth. So if you've got more atoms, if they're more densely populated together, it's going to take longer to get through each one, right? Imagine going to the airport, and if you had no security checkpoints, right? You're in the vacuum of space. There's no security checkpoints to get through. You go right through, and it's no problem. But all of a sudden, you go there, and for whatever reason, something happened, and now you have to go through 5 security checkpoints. It's going to take a lot longer to get through because you have to get processed through more and more things to get to where it is that you want to go. Okay, so those are transparent objects. What about things that aren't transparent? What about things that are opaque? Okay. Well, things that are opaque, they still have the light come in, they still hit the atom, but instead of jiggling the electrons to make another photon to spit out to the next place, it simply just absorbs that photon, it absorbs the energy that's associated with it, and we change that energy, right? Because energy is not just created or destroyed. It has to just move from place to place. So if we have light energy that comes in and it gets absorbed by that molecule, it has to turn into some other form of energy. And the form of energy that it turns into is kinetic energy. Well, we just talked about in thermodynamics that if you increase the kinetic energy of the molecules, we also say that you are increasing the temperature of the substance. So that's why if you have something that is, say, black, it's going to absorb a lot of light energy, and that light energy is going to get converted into heat energy. So things that are black tend to hold more heat and they warm up quicker. Okay? Different colors throughout that spectrum are going to absorb different frequencies of light, and it's going to change the amount of energy that it stores, and it's going to change the amount and the rate that it heats up based on that light coming in, right? So this is one of the reasons if you're out on a sunny day versus a cloudy day, it could seem very similar in temperature, but on a sunny day, you're almost going to get that sunburn a little bit more. You might feel a little bit more dehydrated throughout the day because you've got more of those light rays coming down and hitting you, as opposed to on a cloudy day, you're not having as many of those light rays coming in from the sun, passing through the atmosphere and getting to you. So that's the big difference between an opaque object and a transparent object. All right, that's it for today. We will continue on our discussion looking at this spectrum tomorrow. We will take a look specifically at this visible light section, and we'll expand that out and really start talking about what color is, and really trying to figure out some very interesting things about color and how it works and why it works and why we see some of the things that we see in nature. So, all right, that's it for today, and I'll talk to you guys next time. All right, bye.